And the next talk is by Zhi. Take it away.
Hello, everyone. Thanks for sticking around for the last afternoon instead of going to the beautiful ocean. Really appreciate it. I'm Zhou from University of Rochester. Today I'm going to talk about how we use fat pointers to enforce temporal memory safety for C. This is a joint work with John Criswell and Michael Hicks. So this is from Apple's latest security update. It reports a vulnerability that might lead to arbitrary code execution with kernel privilege, so pretty high severity. And it's caused by a use-free issue, which is a temporal memory safety bug. And if we search use-free in my trace vulnerability database, it shows tons of, and it is growing every day. So temporal memory safety bugs are abundant in C and C++ programs. Conceptually, it is pretty simple. We have a pointer pointing to a memory object. After the object is freed, the pointer becomes dangling. And if we dereference the pointer now, it's a use-free bug. And if we free this pointer more than one time, it's a double free bug. And the situation gets particularly dangerous when the freed region is reallocated and filled with new valid data. Then the dangling pointer might leak information or corrupted data. So to prevent this problem, an effective solution called dynamic ID or K-lock checking. The high-level idea is like this. At memory allocation, we assign each memory object a unique identifier, which is also called a lock. And we assign the pointer to the object the same ID, which is also called a key. And at memory deallocation, the lock is invalidated to a value that will never be used for any key. And for pointer dereference, the runtime checks if the key matches the lock. So pretty straightforward idea. It dates back to the 80s for the dialect of Pascal. And many previous works tried this idea for C. However, one common or two common limitations of previous K-lock checking approaches are high performance overhead and low entropy for the keys, which means the keys space is low and it's not secure. So one key observation we got on why many of the previous K-lock checks are slow is that they maintain the metadata, which is a key and a lock, in disjoint memory region, which means the runtime must first locate the metadata for pointer checking and the pointer propagation. And this lookup procedure is slow. So this led us to choose in-place metadata, which means we want to keep the key close to the pointer and we want to keep the lock close to the object. Also, several previous work tried this idea. One option is we can utilize the first unused, most significant 16 bits of a pointer as the metadata. However, because there are only 16 bits, there are too few of them, so we need a key and we need other metadata for locating the lock. So it offers low entropy for keys, which is not secure, and it has difficulty supporting large objects. And it only works on certain 64-bit systems. So our solution is real fat pointers, which means separate metadata besides raw pointers. And we added new fat pointers and new language features instead of automatic compilation strategies to solve the problem of backward compatibility, which I will talk about later. And we build our solution on check C. So before talking about the fat pointers, a bit of background on check C. Check C is a new extension to C, aiming for memory safety and type safety. And it offers a low performance overhead for spatial memory safety, and it gives a good backward compatibility with the legacy code, and it enables programmers to incrementally convert legacy code to check C code. However, it lacks temporal memory safety. And our solution is we add new types of checked pointers to check C, which enforces K-lock checking approach. So let's take a look at the pointers. In C, a raw C pointer is usually implemented as a single word integer. And our checked pointer has two metadata, a key, as mentioned earlier, and an offset, which is used to compute the location of the lock. So let's say an example. Here we have two pointers. One points to the first element of a struct, and the other points to the last element of the struct. And the lock is stored right above the memory object. So, and the key is together with the raw pointer. So the first pointer always knows where to find the key and the lock, so it can do keylock checking easily. But for the second pointer, because it points to the middle of the struct, it needs a way to find where the lock is. So the offset is the distance from the raw pointer to the beginning of the object. So the runtime can simply subtract the offset from the current raw pointer to compute the location of the lock. So the temporal memory safety check would be straightforward because the compilers or the runtime knows where to find the key and where to find the lock. So that's the new checked pointer. Let's say a potential issue with this design. So perhaps the biggest concern or complaint about fat pointer-based approaches is memory layout compatibility with legacy library code. The problem is that legacy library is unaware of the structure of the new fat pointer. So here, for example, we have a library function that takes a pointer to an array of m pointers pointing to characters. And in memory, it looks like this, all pointers sitting together. However, when we have an array of checked pointers, in memory, we have all the metadata interspersed between the raw pointers. So the library function would now misinterpret this array of checked pointers because it would incorrectly assume the metadata to be pointers. So if we want to keep the legacy library intact, then an array of pointers must be presented without metadata in between for the library to use. And to solve this problem, there are several options. First, we can use raw pointers for such arrays. This is possible because in checkc allows mixing raw C code and checkc code at a very high granularity. So we can do that, but it's less secure. Or we can use a hybrid mode of some pointer using in-place metadata, some pointer using raw pointers, or some pointers using disjoint metadata. But the implementation would be very complex, and the disjoint metadata incurs high overhead, as I mentioned earlier. So our solution is pretty straightforward. We do data marshalling. It means before calling a library function that takes a pointer to an array of pointers, programmers needed to add calls to our marshalling API to extract all the raw pointers from the array of checked pointers and reassemble them into an array of raw pointers for the library to use. And after the call, programmers can optionally call the unmarshalling procedure to recover this array of checked pointers. So pretty straightforward. However, there are two potential questions. First, because this procedure requires programmers' manual intervention, we want to know how much program effort is required. The second, this looks like a lot of data movement involved. So what is the performance penalty for that? If the answer to any one of the two questions is very high, then this would not be a practical solution. So to answer these two questions, we did two measurements. We analyzed all the 8 C programs from the 2017 spec benchmark suite, plus 8 large open source C programs. First, to answer the first question, we measured the number of function calls to library function that takes a double pointer type arguments. This roughly represents the number of call sites that require programmers' manual intervention. And here's the results. For most programmers, such call site, there's only a few of them, I would say, considering the size of the program. And the largest is 383 from the Apache's HTTP server. But consider that it has over 200,000 lines of code. We believe this it is still manually manageable. And to answer the second question about the performance penalty for the data marshalling, we ran the programs and measure the the size of the shared arrays between application and the library. And the largest the size of the largest shared array of pointers between application and the library is only 300 kilobytes, also from HTTPD. So with this result, we believe that our solution is scalable and manageable. So next, about evaluation, we implemented the new checked pointers by extending the checkc compiler, and we did a standard data flow analysis to remove redundant pointer checks. And we measured the performance and the memory overhead, and we compared our solution with the SETS, which is a disjoint metadata key-lock checking mechanism that provides the same level of security as ours. And for benchmarks, this is tricky because we need to manually port raw C programs to our check C programs. So it's impractical for us to do a lot of large programs. So we choose Odin, which is a small benchmark suite, but it is pointer intensive. And all previous memory safety work show that they incur significantly higher performance overhead on their pointer intensive benchmarks than other programs, which is understandable because memory safety work revolves around manipulating the metadata of pointers. And we also ported 4 real-world applications and 1 pointer-intensive benchmark of spec 2006. And here's a result. To summarize, for a lightweight HTTP server and for curl, which we ported the HTTP protocol and the engine part and leave the other untouched. The overhead is almost negligible, and for a lightweight JSON parser and a data compressor, the overhead is around 10%. And for Odin, our overhead is 29% overhead. It's not a small number, but remember that Odin is pointer intensive, so it represents a pathological situation for your programs. And in contrast, SETS overhead on Odin is 92%, while SETS overhead on spec 2006 is 45%. And for this MCF program, the overhead comparison is 64 versus 175. And the main reason for this giant performance gap is that how the two approaches locate the metadata for point validation and propagation. So here's the comparison of the key-lock checking procedure for dereferencing a pointer argument. And in our approach, we only use this 1 load, while SETS uses 4 loads. And because a load instruction is already 2 orders of magnitude slower than a lightweight bitwise or arithmetic operation, this explains the giant performance difference. So to conclude, we add 4 new types of fed pointers. I only introduced the one due to time limitation, but we added 4 new types of fed pointers to check C for temporal memory safety. And it is fast and it is memory efficient, and it provides comprehensive memory safety, meaning detecting all types of temporal memory safety bugs for both heap and stack. And it gives manageable backward compatibility with the legacy libraries. And the takeaway message is we believe fed pointer can be a practical solution to temporal memory safety for C. And there's a lot more in the paper, like temporal memory safety for stack objects, and our porting experience, detailed comparison with related work, and more. And we open sourced our compiler and the whole tool chain, including the evaluation scripts. So if you use our tool and have any questions, problems, please don't hesitate to contact me. And lastly, I am on the job market this year. If you are interested in talking to me, I'll be happy to talk about it. And I'd be now take questions. Thanks.
Right, so again, okay, let me not ask my question. Let's do audience questions instead. Would you guys come up front? Yeah, just introduce yourself.
Hi, I'm Matt Parkinson from Microsoft. I was just interested in concurrency because...
Excellent question. No, currently we don't have. Yeah.
Yeah. Hi. I just wonder, how did you remove the redundant checks?
It's a pretty standard data flow analysis. So basically, before each and after each basic block, you collect which pointer just got checked. So if you're pretty sure this pointer just got checked, and inside of the basic block, you don't have any changes to the pointer, like it doesn't call external library functions, or it doesn't have a double pointer writes, then you are sure after that it is alive, and you can remove redundant checks.
Okay, so no alias analysis since.
No, yeah, but alias analysis will definitely improve the precision and remove more. Yeah, currently it's a very basic standard data flow analysis.
Okay. Okay. So for the performance evaluation, did you include the checked zero notations in your evaluation, or only your like new extensions?
What do you mean the annotations?
Like the checked Z is original annotations to the code.
Oh, yeah, we have a related code. In the paper we have a column listing the number of new checked pointers we added and the number of calls to our secure API for memory allocation and deallocation. We have such three data in the evaluation section.
Hello, thanks. I can see how your marshalling the arrays of pointers works nicely for interacting with legacy libraries that read the data. How much more complex is the marshalling when those legacy libraries are modifying the pointers?
How complex is the API?
Yeah.
We have it looks like this. So yeah, this is the API. So basically, if you have an array of checked pointers, you pass this array of pointers as arguments to our marshalling API, and it's pretty straightforward. It's just extract all the raw pointers one by one from the array of checked pointers and reassemble them into a new array, and then the API internally passes the pointer to this array of raw pointers to library function. That's all. It's pretty straightforward procedure.
Okay.
But if you want to talk more, we can talk.
Oh, I'd like that. Yes, please. Thank you.
All right, let's thank the speaker again, and Fang's up next.